Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we're going to be talking about mathematical induction. In fact, this is our last Thursday Tidbit for 2021, so stay tuned on this channel if you want to see what's coming for the new year in 2022. As always, if you like this, please subscribe and check out our other content we have on our channel too. But let's get started and take a look at mathematical induction, and let's start with a simple example. Let's look first at the sum of odd numbers. So we want to add up the first k odd numbers. What do we get? We might start with 1. That's of course just itself is 1. But let's see if we can look for a pattern here. So 1 plus 3, of course, this is going to be 4. Well then, what if we continue looking at this? 1 plus 3 plus 5, so now we have 4 plus 5, this is 9. And we can continue on in this manner. So we have 9, we have another plus 7 in this case, so this will get us to plus 16 next. And finally, at least for this example, we have a 25 here. Now, some of you probably are already seeing the pattern in this case, but let's take a look at this here and see if we notice anything special about all of our numbers. Well, we actually have 2 squared, then we have 9, which is 3 squared, 16 is 4 squared, and 25 is 5 squared. So a lot of math is looking for patterns like this, and then you can turn those patterns into guesses. So if we want to summarize this on the next page here, what is the pattern? Well, our guess is that if we add up these numbers, so 1 plus 3 plus 5 up to 2k minus 1 in this case, our guess would be that we want to get k squared in this scenario. So you might need to look back at those examples, just make sure this matches a little bit. But for example, if k is 5, that was our last example there, because we had 1, 3, 5, 7, 9, the first 5 odd numbers. They added up to 25, which was k squared in this case. Now, on a math contest, or if you're doing this that way, we can be pretty confident that this pattern is correct. But we haven't proven this fact. This isn't something that we've now said, oh, now it has to be true forever. There's some fun examples of things that are true for a long time until they're not. So part of mathematics is, when is something true? How do we prove some of these statements that maybe involve infinite numbers like this here? Now, as you probably can guess, induction is a tool that is going to help us with some things like this. And an easy way to get started with induction is to think of it as a tool or principle that does help turning patterns like this into proofs. And we'll see that in the more formal statement as well there. But general idea, we look for these sum of odd numbers, we find a pattern, and then induction can be a way to prove that that pattern is true forever. And that can be useful for remembering what induction is useful with and also help remembering its statement. So a little bit more formally, so the medium formality here is if something is true at the start, and then if you know it's true for one value, you can prove the next value. So this is the pattern type of thing. You start at the beginning, it's true, and then what you want to do is that you want to prove that that pattern continues. So this second statement, which is another if statement there, right? If it's true for one value, then it's true for the next. You can think about that as saying the pattern continues, right? Then it's true for all values in this case, right? So more formally, so we did the rough idea, a little bit of formality. Now the more mathematical way of stating this, if we have a statement P of n, so this is a statement that is true for the integers or positive integers, things like that, right? If P of 1 is true, so if we're doing this for the positive integers, we have our base case, it's true at the beginning, it's true at the start, and then if you know it's true for one value, arbitrary value, this isn't saying you prove it for 5, 5 proves 6. This is saying you prove it for n, or if you know it's true for n, then you prove it for n plus 1. This is called the inductive step there. Now these proofs look a little bit like magic sometimes, but let's practice writing out two of them, two slightly different ideas or slightly different proofs, and see what it gets us. First one we can look at is, of course, the pattern we are just talking about here. So we want to prove that 1 plus 3 plus 5 up to 2k minus 1 is k squared. So what is our base case in this scenario? Right, so we want to prove that this is true at the beginning in this scenario. So here, for example, we could say, what happens when k is 1? Well, 2k minus 1 is 1. So 1, is this equal to 1 squared? Well, yes, it is. So we have our base case. If you wanted to check this for a couple more, well, we actually already did this. But the formal induction proof only needs a single base case to start from, and then we'll prove that it continues to work. But we already checked that this is true for 2, 3, 4, 5, etc. that way. So this inductive step is the one that allows us to show that this pattern continues and show that this keeps working in this scenario. So here is where it seems like a little bit of magic in this case. So for the inductive step, we want to assume that it's true for one value. So this is sometimes called the inductive hypothesis. So we're going to assume that we know that 1 plus 3 plus 5 plus all the way up to plus k minus 1, 2k minus 1, we can prove that this is equal to k squared in this case. Now, why does this work? Think of this, it's not magic or anything. Think of this as you have proven it up to a step, right? We checked it's true for 1, 2, 3, 4, 5. Do we have to go back to the drawing board to see it's true for 6? No, we're going to prove it's true in general. You can always go one step further, and that tells you that because you can just keep doing that however long you want, it's actually true for all values in this case. So we know that it's true for the first k values. So what happens if we add the next? So what happens if we add the next odd? Well, wait a second. What is the next odd in this case? Well, the next odd is going to be 2k plus 1. If you like, this would be, right, 2 times parentheses k plus 1 minus 1. Well, after you simplify that, we add 2k plus 1. Well, on the left-hand side, right, so if we add this to both sides in this case, well, of course, on the left-hand side, we get 1 plus 3 plus 5 plus ... And let me just make it clear there that this is then plus 2k minus 1. And then we have our plus 2k plus 1. So that is the one side. But what do we get on the right-hand side? Notice we get k squared, and then we have plus 2k plus 1. So we added this value to both sides, and here's where it does admittedly seem a little bit like magic. It doesn't seem like we do much, but the power of induction is it shows that this actually gives us a full proof. Why? Because what is the right-hand side now? This is the next square. This is exactly what we wanted to prove. This is k plus 1 squared, so this is a complete inductive proof. To clarify, we did the base case, so we did one step, then we did the inductive step. Putting them together gives us a true statement for all values. So then putting these two pieces together, it is important that it's both of these pieces. Putting those two together gives us that this is true always here. So both pieces put together give us our final result that we know. We now have proven this formula. If you add up the first k odd numbers, you get k squared. Okay, now this is often used and first talked about in algebra. It's very famous for proving a lot of these algebraic results. What if you add up the first integers, the first squares, the first cubes? You do a lot of recursive formulas, sequences. There's a lot of great things you can do there with induction. Just as some quick other examples, you can use induction or variations of it that are actually equivalent, so we don't need to worry about that too much, to prove a lot of other things. For example, you can use induction to prove that every integer that's greater than or equal to 2 can be written as the product of primes. We're going to look at that one today. As another fun one, you can prove that any circle divided into regions by n lines can be colored so each region is red or blue and no two adjacent regions are the same color. And again, you can do this as an inductive argument, that you have a coloring that works for n lines. What happens if you add another n line? If you know programming at all, you're probably starting to see a connection to recursion and recursive algorithms and things like that as well. But let's take a look at this primes one as a way to close out this video. And this is actually a slight modification. And so this is sometimes called strong induction, but it's equivalent because we can make a statement like we have here. So our P of n statement for this problem is we're always going to be assuming that every number from 2 up to n can be written as the product of primes. So we're making a slightly stronger statement and proving a slightly stronger statement. Of course, it's equivalent to the original thing there. So base case P is 2. Well, the prime number 2 is prime, so we're done in that case. So our inductive step there, just to clarify this means, again, pretend we've proven it so far. So what can we assume in this case? What is our inductive hypothesis? We're assuming P of n. So we're assuming that we know that every value from 2 up to n can be written as the product of primes in this case. So, right, what if we look at n plus 1? We look at our next number. We know that every number smaller than it works already. Well, look at n plus 1. Well, either it's prime. If n plus 1 is prime, we are done already. And here's where the inductive thing comes from. What does it mean to be not prime? Well, to be not prime, that means you have two factors that are smaller, right? So this tells us that n is actually a times b, where both of these are, right, whoops, not n plus 1 is a times b, where both of those numbers are smaller than n plus 1. So they're n or smaller. In fact, we know that they're smaller than n in that case. But what have we already assumed? We've already assumed for those smaller numbers, right? This isn't written as a product of primes yet, but we know A can be written as a product of primes. And we know its other component B can be written as a product of primes. So what happens if you have a product of primes times another product of primes? Well, wait, that just gives you a product of primes. So again, you might need to write out a little bit more details here, but that means we are done as well. So that is our inductive step where we say that if we already have a bunch of prime factorizations, the next number we come across either is prime, so it has its own new prime, or it's already built up of things we've already shown are written as the product of primes, and that completes our proof. So check out all these other types of ideas, see if you can try other inductive proofs to get used to this pattern of the base case and then the inductive step from there. But that'll do it for this video. As I mentioned at the beginning, please keep an eye on the channel, subscribe for updates on what's to come in 2022. Otherwise, thank you everybody for watching this video and all of the Thursday tidbits from 2021. Goodbye.